Let's take a look at acceleration. Now that's a term that we use in our everyday language, but is not used all the time correctly. The definition of acceleration is the rate of change of velocity according to time. Very mathematical language there, just like we had in the constant velocity video. We'll take a look at that here in a second. Now I have a car down here that's accelerating at 2 meters per second squared because the unit, the base unit for acceleration, is meters per second squared. So what ends up happening, if we start out with an initial velocity of 0, we're going to use the letter U to stand for initial velocity. After 1 second, it is going 2 meters per second. After 2 seconds, its velocity increases another 4 meters per second. That's actually the definition, really, of what's happening with acceleration. For every second, if my acceleration is 2 meters per second squared, for every second, the velocity increases by 2 meters per second. So from 2 seconds to 3 seconds, I go from 4 meters per second to 6 meters per second. Go another second, let the velocity go up by 2 more meters per second. Go another second, let the velocity go up by another 2 more meters per second. Now that has a very interesting effect though on how far the car can travel during that time. Because in the first second here, we were starting out 0 velocity and we sped up to 2 meters per second. So we go a little distance. But in between 1 second and 2 seconds, over the course of that next second, the velocity starts out at 2 meters per second. So we're already going relatively fast. We're already going to go a little bit further. And we accelerate another 2 meters per second in our final velocity up to 4 meters per second. So we go from 1 second to 2 seconds, 2 meters per second to 4 meters per second. That means we're going to go a little bit further, go 3 meters there. Same thing continues to occur. Notice how, because the velocity, the initial velocity between the beginning and the end of that each 1 second period, if we're talking about it, is higher, and we're accelerating as we end with a higher velocity, we're able to cover more and more and more distance with each passing second. Kind of the idea of acceleration. With each passing second, we go faster and we are able to cover more distance. Now, if we were to graph out that displacement data here, what we'd end up finding is a curve that looks something like this. So I graphed it out. After 1 second, we had only gone 1 meter. After 2 seconds, we had gone 1 plus 3. We had gone a total of 4 meters. After 3 seconds, we had gone 1 plus 3 plus 5, a total of 9 meters there. So whenever you graph it out, if you're looking at a position, how far away from the starting point you are, time graph, you actually find a curve. This is an x squared curve or a quadratic. Now, many interesting things actually come from our velocity time graph. If I were to graph out, like I did right here, how fast we were going each second. So after 1 second, we were going 2 meters per second. That's the definition of acceleration, right? With each passing second, we increase the velocity by 2 meters per second. If the acceleration was 2 meters per second squared, I get a nice linear graph here. Now, if you remember back to our constant velocity video, we talked about how the rate of change means the slope. So here, this definition actually is telling us that acceleration is the slope of a velocity time graph. So whenever I write down the slope equation, y2 minus y1 divided by x2 minus x1, I can change the word slope to acceleration, and then I can plug things in. What's the y2? Well, on the y-axis, we have velocity, so y2 must be the highest velocity we get up to, right? So let's actually label that v, standing for final velocity, the highest velocity. y1 is the starting velocity, how far, how in the beginning. In this case, it would have been 0, but we don't always, cars and bikes and people and planes and everything doesn't always start out with an initial velocity of 0, so let's give that a letter 2, u. And then x, 2 minus x1. That's the change in the time, because the time is what's on the x-axis. What's on the rise, the y-axis? Velocity, a change in the velocity. On the x-axis is a change in the time. So let's make this time 2 minus time 1. And then generally with times, we just go ahead and we reduce a time 2 minus a time 1 into just simply time that passes with a t. And we have derived for ourselves the acceleration equation. In fact, let's do a little bit of side work maybe over here to make sure that this equation is right, because we know our car was accelerating at 2 meters per second squared. So let's plug things in. A equals the final velocity that we got up to was 10 meters per second, and the initial velocity that we started out at was 0. So let's actually plug that in. I got 10 minus 0 divided by how long did it take? Well, it accelerated over 5 seconds. So divided by 5. A equals 10 divided by 5. A equals 2 meters per second squared. And that is exactly what I was anticipating here, because that is what I declared the acceleration of the car to be. Now there's something else cool that happens on velocity time graphs. It's how you can get the displacement here. So imagine me drawing a line straight down like you see right here, just to the x-axis. If it was negative below the x-axis, I'd draw a line straight up to the x-axis. Now, there's some area here, so let's kind of shade that. This area right here, right? It makes a shape. This is a triangle. So the area underneath the line to the x-axis, in this case, makes a triangle. If we look at that triangle, area of a triangle equals 1/2 base times height. Well, we know that, right? We can calculate that. 1/2 times my base is 5, and my height is 10. So let's see what this turns out to. The area equals 1/2 times 5 times 10 is 25. Is that something that we know before? Well, yeah. The total displacement that the car traveled was 25 meters. This actually leads to another thought with velocity time graphs. Area under a velocity time graph is your displacement. Let's actually summarize all those ideas, make sure that we've got 3 key concepts that we discovered on this slide. First off, we discovered the equation for acceleration, the base equation for acceleration. Acceleration equals the final velocity, v, minus the initial velocity, u, divided by time. Make sure you don't get confused about what v and u stand for. Final velocity, how fast we end up going, minus initial velocity, how fast we were going at first. Second main concept, the slope of a velocity time graph is the acceleration. And the third one, the area under a velocity time graph is the object's displacement. Let's quickly talk some comparison between graphs now that we've done constant velocity and acceleration. Now, the positive constant velocity was one of the first things that we talked about, right? In positive constant velocity, a position, x, a position time graph, the graph goes up linearly if it's a positive constant velocity with a positive slope. If we were to graph out a velocity time of this, it would just be flat at one velocity because it was constant. So if the car was driving at a constant velocity of 2 meters per second, this slope would be positive 2, and this flat line would be at 2 right here. It's the same thing for negative constant velocity, aka going backwards. Positive constant velocity, the car is driving this way at 2 meters per second. We declared to the right to be positive. If it's a negative constant velocity, it just means the car is in reverse, driving the direction that we called negative to the left in this case constantly. So the slope would be going down. We would be losing position here. Negative 2, let's say, for that slope. And the velocity would have to be underneath the x-axis, lined up with negative 2. Now, truthfully, this line right here could actually occur anywhere for both of these. In other words, in these examples, I drew it up above the x-axis, but this could be down below the x-axis. We could already be starting at a negative position, not at, let's say, if this is the 0 mark, the car could already be negative and moving even further negative. All right, looking at acceleration, here are the graphs that we just did. In a position time graph, you end up for a quadratic with going up, because as you accelerate there, you're going to cover more distance or more displacement. You're going to have a greater position, cover more distance as time goes along. So it actually curves up if you have a positive initial velocity. So I was going to the right and I accelerate to the right. In this case, I go both ways. That's going to give me more and more displacement. My velocity time graph, velocity starts out low and goes up, and the slope of this velocity time graph is my acceleration. Now there's actually another side to this. All I did was move my little gray box over to show the other side of the quadratic. This is what we're used to seeing from the last slide, but what about this side of it? Whenever we have a negative initial velocity, so maybe the car is in reverse right now, was already going backwards, but then hit the brakes to try to slow down, or hit the, this would be a terrible way to do it, but hit the gas there, and so start to accelerate forward. What ends up happening is we have a negative initial velocity. Notice the slope coming down kind of like this, but we are slowing down in that case, decelerating back towards zero. This graph over here shows a positive initial velocity with a negative acceleration, aka deceleration from what we traditionally think. We are going forward to start out with some positive velocity, and we hit the brakes, so the acceleration vector points the opposite way, trying to slow us down. Our velocity time graph starts out with a high velocity, but we're hitting the brakes where we have a negative acceleration, and so the velocity goes downwards. Now there's another side to this, of course, as well. Let's slide that box over. Negative initial velocity. If we have a negative initial velocity as well going on, let's erase this and this velocity vector over here, draw in the velocity vector coming back this way as well, then we're going to actually accelerate in the negative direction. We could even maybe join on this graph and draw it going down. That way the velocity gets greater and greater and greater in the negative direction. Let's do a few example problems. In two of them, I'm going to use the equation for acceleration, and in two of them, numbers 3 and 4, I'm going to deal with the graph. Number 1, a car accelerates from a red light from rest. That's critical. From rest here means u equals 0. We're accelerating from rest for 7.3 seconds. There's a time. T. Calculate the acceleration of the car. So we're looking for A. A equals question mark. If it ends up going 21 meters per second, there's my final velocity, V. So I put everything into a variable bank just so I can separate out the data that I had underlined from the word problem there and labeled. I double check my units. Looks like we're all in base units. I rewrite my equation and then I substitute in. So I'm going to put 21 where the V is, 7.3 where the T is, 0 where the U is, and the A is the question mark, so I'll leave that an A. The last step would be to work the algebra, but look, the A is already by itself over here. The unknown variable is, so I don't have any algebra to work. This is just type in the calculator. I find out that this turns out to be 2.87, or with significant figures, 2.9 meters per second squared, because the base unit for acceleration is meters per second squared. All right, number 2, a different car going 25 meters per second. Now it's already going 25 meters per second. This is going to be my initial velocity. Then something happens. Slams on brakes to stop. Stop here means 0. We're trying to stop. So slams on brakes to stop. This is the final velocity. This is how fast we end up going. Stop at a red light. Calculate how long. How long means we're solving for time. T equals question mark. Will it take the car to stop if the brakes provide a deceleration of negative 4.8 meters per second squared? There's my A, deceleration. That's why it's negative. So I make my variable bank over here, pulling all the data out. I rewrite my equation. I check my units. Yep, base units, velocity 0 meters per second, base units there. And then I substitute everything in like I just did. A was negative 4.8. The final velocity, we're trying to stop, right, is 0. And so I put a 0 where the V was. The initial velocity was 25. So I put a 25, and now let's solve for T. The algebra here, to be able to solve for T, the very first thing I got to do is get the T out of the denominator. So let's multiply T over to the other side here. I went ahead and multiplied it over, and so now I have negative 4.8t equals negative 25, because 0 minus 25 is negative 25. Last step here, I've got to get the t by itself. So I'm going to divide both sides by negative 4.8. And I turn out with 5.2 seconds. Positive, right? Negative divided by a negative gives me a positive, and time should always turn out to be positive. Let's look at the graph in numbers 3 and 4. It looks like, according to the graph, I've got an object that must be decelerating. It starts out at some higher velocity, 10 meters per second on this velocity time graph. Always check your axis. Whenever you have a graph, look to see what type of graph it is first before deciding what you need to do. Velocity time in this case, and it's slowing down. Number 3, determine the acceleration of the object described in the graph above. Well, since it's a velocity time graph, I remember that the slope of a velocity time graph is the acceleration. So let's pick our data points and let's just plug into the slope equation. y2 minus y1 divided by x2 minus x1. Now be very careful. Up here is point number 1 and down here is point number 2. So make sure you know which way you're going. We're expecting a negative acceleration, a negative slope. So whenever I substitute all of those things in there, right, my y2 up here, or down here, excuse me, was 0 minus my y1, 10, right? And I keep going, right? We go from x2, 4 to x1, 0. There, I come out with an acceleration of negative 2.5 meters per second squared. Oop, made a mistake on the unit. Let's fix that really quick. Number 4, determine the displacement traveled by the object in the graph above. Remember, displacement is the area under a velocity time graph, or the area between the graph and the x-axis. Hey, that looks like a triangle there to me, which means what we need to do here is find the area of that triangle, 1/2 base times height. That's 1/2 times the base of this triangle looks to be 4, and the height of this triangle looks to be 10. So 1/2 4 times 10, that turns out to be, my displacement, S, is going to be 20 meters. All right, guys, go back, digest this video as need be, go and pause, rework problems, maybe cover up the work that I did, try it yourself, see if you are able to do it the same way, get the same answers, and we'll do a few more example problems and plenty of practice in class.